We go on to the topic of piecewise functions. These are sometimes called case functions. A piecewise function is one where the definition of the function changes depending on what interval of the domain we're talking about. So what I've drawn here on the right is a function that seems to be just kind of a random collection of different functions that you may know, and we're going to try to write this as a piecewise function. So let's use this color. So you recall with a piecewise function, we're going to write it with a big bracket like that and write the different parts of the definition in different places. So first, let's take a look at the left side of the function. We see what this is it's going to be a line. It's a line. We can see that it's a line that's positively sloped, and although it would be possible to have a more complicated line here, what we can easily see is that for every unit that this function moves to the right, we see that it goes from -1 to the x-axis, that's 1 unit horizontally, it rises 2 units. So the rise over the run is going to give us a slope of 2. So that gives us a slope of 2 and a y-intercept. We see that it intersects the x-axis at 2. So there's a lot of 2's there, but this function is going to be y equals 2x plus 2. We then have to say where that's valid for, and we can see that it's valid for all x values that are less than or equal to positive 1. So this is for x less than or equal to 1. And we know that it's going to be less than or equal rather than just less than, because as we can see there's a solid dot here, meaning that this definition applies to the actual point x equals 1. And it's when we get to this curve here that we see that the endpoints are excluded. So now let's go to the curve itself. Hopefully I've drawn this. It should be intersecting the x-axis. This is what you see on the right is a parabola. I don't want to imply that I don't want to imply that every curve like that is a parabola, but I'm just going to tell you for the purpose of this example that what I've drawn is in fact a parabola. And you can see that since it's basically the shape of the standard parabola y equals x squared, but it's shifted by 2 units to the 2 units to the right. Well, we know how to shift a parabola 2 units to the right. If I say that f of x equals x squared, then shifting 2 units to the right is just going to be f of x minus 2, so that equals x minus 2 squared. So this is going to be x minus 2 squared for the interval 1 less than x less than, sorry, I forgot to put this number in when I wrote the example. This is going to be 3, like that. So for 1 less than x less than 3, that gives us the equation of that part of the function. And then finally, if you look down here, for all values that are greater than or equal to 3, the function is simply the constant function -2. So I'm going to write -2 for the values x greater than or equal to 3. And there's our piecewise definition of the function that I've drawn. So you sometimes have to solve these in either direction. Either you see the diagram and you have to come up with the definition of the function, or you're given the definition of the function and you have to graph it. Regarding this parabola, normally, of course, I was able to tell you, since I'm talking, I was able to tell you what function this was, but of course, if you were reading this in a book, they would give you a more precise definition of what a shape is so that you could work with that. So I want to move on to the topic of absolute value functions and their relationship to piecewise functions. The thing you have to realize is that in every absolute value function is sort of built in a piecewise function. We all know what the absolute value of x function looks like. If I write y equals the absolute value of x, I get a function that looks something like this. It's v. So it's really going to be just on the right side, it's going to be the line y equals x, and on the left side, it's the line y equals -x. That suggests to you how you might write this as a piecewise function, because what we can say is that f of x just equals x for x greater than or equal to 0, and -x for x less than 0. By the way, I've sort of arbitrarily assigned 0 to the easier definition. I could have written that it's x for x greater than 0 and negative x for x less than or equal to 0. There's no particular reason you couldn't say that. It's just sort of by convention. You assign the transitional point, which is 0 here, you assign it to the easier one of the two definitions, or you can just pick either of them if neither of them is easier. So we can use this fact to, first of all, let me just change this a bit. We'll say that the absolute value of x is actually equal to this piecewise function. So we can use this principle to rewrite more or less any absolute value expression as a piecewise function. So I've put up two examples here. Let's write each of these functions as a piecewise function. So first of all, f of x equals x squared minus 1. What we can do is say that this is going to be x squared minus 1. It's going to equal various different things depending on whether x squared minus 1 is greater than 0 or less than 0. So it will be x squared minus 1 for all values of x for which x squared minus 1 is greater than 0. So we need to actually solve that. Say x squared minus 1 is greater than 0. Well, there are a couple of ways you can do this. You could do it algebraically, or you could simply observe that this is going to be greater than 0 whenever x squared is greater than 1. So x squared is greater than 1. That's going to be true whenever x is greater than 1 or x is less than negative 1, because of course once I square it, the positive and negative don't matter. It's only the magnitude of the number that makes any difference. If you found this at all confusing, you could simply graph x squared minus 1 and see that it looks like this, and see that we're actually below the x-axis only when we're in between negative 1 and 1. So we can say is that x squared minus 1 this applies wherever x squared minus 1 is greater than 0. So that's going to be for x is less than negative 1 or x is greater than 1. And actually, since it's going to be 0 at those points, I can just put equality in into the definition. And then finally, if x squared minus 1 is less than 0, then I simply have to take the negative of that expression. So that's going to give me 1 minus x squared. Where did that come from? Negative x squared minus 1 equals 1 minus x squared. So that's going to apply between negative 1 and 1. So there's a piecewise definition of that function. Now let's do a slightly more complicated one. Oops, I meant to put absolute value around that. So here what we want to do is write this and say absolute value of 2 minus 3x is going to equal some piecewise function. So we need to know when 2 minus 3x is greater than 0. So that's going to give us 2 is greater than 3x, just moving the negative 3x over to the other side, or adding 3x to both sides of this. So that gives me 3x is less than 2, or x is less than 2/3. So what I can do is say that the expression is going to be 2 minus 3x whenever x is less than 2/3. And that means that it's going to be the negative of that. 2 minus 3x is equal to 3x minus 2. So that gives me 3x minus 2 whenever x is greater than 2/3. And I can simply choose either of these to act for the endpoints of those intervals, put equality on just one of them, and that gives me a piecewise expression for this absolute value function.